Hey, I'm Mitchell, and welcome to another video in the RSP Education series. Imagine an entire factory floor running like clockwork. You got robotic arms assembling parts with precision, motors whirring, sensors monitoring, controllers making split-second decisions. But have you ever wondered, how do all these machines actually talk to each other? Today we're diving into the very language of automation, from serial and parallel communication to analog and digital signals. Synchronous versus asynchronous data flow. We're going to break down the building blocks that keep modern industry moving. Whether you're an engineer, a technician, or just automation curious, understanding how communication works inside these complex systems is key to unlocking better performance, faster troubleshooting, and smarter designs. If you like this kind of content and want more educational videos, please like and subscribe. Also, this video is for educational purposes only. Always consult a professional for your application, as RSP Supply is not liable for any misuse of this information. With that said, let's get right into it. So let's talk the basics of communication and automation. In industrial automation, communication is how different devices like sensors, controllers, and actuators share information to keep a system running smoothly. This happens through data transmission, which is simply sending and receiving data between devices. There's a couple of different data transmission concepts. First off, we got serial versus parallel communication. When we talk about sending data, there's two main ways to do it. There's serial communication and then there's parallel communication. So for serial communication, data is sent one bit at a time over a single wire. It is slower per cycle, but it works very well over long distances with fewer wires, just one. It's very common in industrial automation. It runs with RS-232, RS-485, Modbus, CAN bus. Think of it like cars going one after another on a single lane road. Parallel communication is a method of transmitting multiple bits of data simultaneously across multiple channels or wires. In a system, in industrial automation, this approach was historically used for high-speed, short-distance communication between components within control systems. However, due to limitations in scalability and noise interference, serial communication has largely replaced parallel communication in most automation applications. Now let's talk synchronous versus asynchronous communication. In industrial automation, devices like PLCs, sensors, HMIs, controllers, they all need to communicate, and this communication can efficiently happen in two main ways. That's synchronous and asynchronous. For synchronous communication, it's clock-based communication. Both sender and receiver follow a shared timing signal, or a clock. Data is transmitted in a continuous and predictable manner. Faster and more efficient because there's no delays between data bits. It's going to be used in high-speed industrial networks like Ethernet IP, Profinet, and Synchronous Serial Interface, or SSI. Some examples of it being found in automation: you have a PLC that's communicating with a motor controller using Profinet. The PLC and controller follow a synchronized clock, and this ensures smooth and real-time operation. For asynchronous communication, there's no clock signal. Devices send and receive data independently. Each data packet starts with a start bit and ends with a stop bit to signal the beginning and end. Slightly slower than synchronous communication because of the gaps between transmissions. Used with RS-232, RS-485, Modbus RTU, and most serial-based industrial protocols. An example of this in automation: let's say you have a SCADA system that's retrieving sensor data from a remote RTU over Modbus RTU. The data is sent in packets without a clock signal, making it flexible but slightly slower. So which is better for industrial automation then? Synchronous communication is preferred for real-time, high-speed control systems like robotics, high-speed conveyors. Asynchronous communication is better used when flexibility and compatibility are more important, especially over longer distances. There's going to be slower data transfer, and it's going to be used for monitoring remote sensors, for example. Both methods are essential in automation, depending on the system's needs. We got analog versus digital signals. In industrial automation, communication between devices like PLCs, sensors, actuators, and controllers, it all happens through signals. These signals can be analog or they can be digital, and different industrial protocols are designed to handle them. So about analog signals, they are continuous signals that can take any value within a range. It's used to represent real-world variables like temperature, pressure, speed, or voltage. It's typically measured in 4 to 20 milliamp current loops or 0 to 10 volt voltage signals. It's going to be more precise, but more susceptible to signal noise and interference over long distances. So examples where you're going to find this in industrial protocols. You'll find it with HART, stands for Highway Addressable Remote Transducer. So a protocol that allows both analog 4 to 20 milliamp and digital signals to be transmitted simultaneously. Modbus RTU with analog inputs. So you'll have a PLC that can read analog sensor data using Modbus RTU, where an analog to digital converter translates the signal. Digital signals are used for binary operations like switching machines on and off, or detecting object presence, or sending encoded data. It's less sensitive to interference. It makes it a lot more reliable for long distance communication. Examples of digital within industrial protocols: Modbus TCP and IP and RTU. They transmit digital data over Ethernet or serial communication. Ethernet IP and Profinet, used for high-speed digital input-output in PLCs and industrial networks. Which is better? Analog signals are better for precise measurements like temperature and pressure. Digital signals are better for reliable, fast, and noise-resistant communication, like motor control or industrial networking. Modern industrial protocols, they favor digital communication, but analog signals are still widely used for sensor measurements that require accuracy. All right, let's do a quick recap. We explored the fundamentals of how industrial devices communicate, the invisible threads that keep automated systems running smoothly. We broke down serial versus parallel communication and learned why serial is the go-to industrial protocol for long distance and reliable data. Then we tackled synchronous versus asynchronous communication and how the presence or absence of a clock signal is going to impact speed, timing, and reliability in your systems. Finally, we compared analog versus digital signals, showing how each has its strength depending on the application. Precision measurements for analog and fast, noise-resistant control for digital. Whether it's a robotic arm, a pressure sensor, or a motor controller, understanding how these devices share data helps you build better systems, troubleshoot faster, and make smarter design choices. For hundreds of thousands of industrial automation products, go to our website. That's rspsupply.com, the internet's top source for industrial hardware.